Okay. Hello, everyone. My name is Maksims Kazijevs, and today I'll be presenting my master thesis titled Deep Imputation of Missing Values in Multivariate Time Series Health Data. I wanted to thank my committee members, Dr. Samat, Dr. Erdemir, and Dr. Rogers, for working with me and for their guidance throughout this work. So for the outline of this presentation, we're going to have motivation behind the work, background and literature review, problem statements, contributions of our work, methods, results, conclusions, and the references. So the motivation behind the missing value problem is that it's a real-world problem in data and data science because machine learnings are not operable on the data with missing values. And if people are choosing random technique to impute the missing values, we don't know what's happening to our data quality and what would happen to our downstream tasks, such as classification or regression, for example. Missing values can happen, for example, in the medical centers where patient data is collected throughout the time, and it can introduce missing values, as well as electronic sensors where the data is collected from the cyber physical systems. If there is a sensor failure, we can have the missing values as well. For the current approaches, people are using random strategies, arbitrary strategies to impute missing values. And of course, the data quality of imputed data quality cannot be as good if we use random strategy. In the AI literature and the research, people are using complete data sets that are far more realistic from the real world data, and they're just ignoring missing values. And imputation problem is mainly studied in the biostatistics and have not been studied in the deep learning a lot. Andrew Young, who is the founder of Google Brain and Deep Learning AI, basically said that we have the models and the codes for many applications. At this point, we just need the data to work with these models. So now we're going to be talking about the background review. First, we have the cross-sectional imputation. First of all, in the cross-sectional imputation, we're dealing with a static data. We don't have the time series variables. One of the approaches, we can use other samples to impute the missing values, for example, as in k-nearest neighbor algorithm, where we can impute the missing value from the similar samples. For example, on the figure on the right, we can see that the blood pressure of Jack is missing. We can use the information from John to impute that missing value. As well, we can use other variables to impute the missing values. If we take the same example, we can use the heart rate of our patients to impute the blood pressure of Jack in this case. And to impute the missing values, we can use other known variables as a function. And research mostly deals with a cross-sectional imputation, where we have feature dependencies. Next one, we have time series imputation. In this case, a sample is observed over a period of the time, or we can call it time steps. For example, right now, the John sample can have, in this case, it has 3 time steps, Monday, Wednesday, and Friday. And in addition to cross-sectional dependencies, we have the time dependencies as well. So in time series imputation, we have the time dependencies. And on the figure on the right, we have at this time, we have the collection of the data that is observed over a period of time. Next one, we have the hybrid imputation, which is the combination of time series and cross-sectional imputation. So now we have 2 components together. In cross-sectional imputation, we have the feature dependency, and in the time series imputation, we have the time dependency. We're going to talk about the time series models as well. Mainly, they were proposed to capture time dependencies and to predict some value in the future. For example, if we have heart rate from Monday through Thursday, we can predict what's going to be the heart rate on Friday. Similarly, we can estimate the missing values. For example, if we have the missing value on Wednesday, we can use the information from Monday to Tuesday to impute the value on Wednesday. We're going to talk a little bit about the data. So we have electronic health records and biomedical sensor data. Medical centers archive patients' data in electronic health record databases, and this data can be used to answer unsolved research questions. For example, people have predicted the real-time mortality. They have estimated the blood and arterial pressure, and they even estimated how long the patient is going to stay in the hospital. However, the collection of the data process is very complex because patients can do the tests or capture their vitals at different intervals at different days, which can introduce the irregularity in the data. And not all the vitals can be measured at the same visit, which will introduce the missing values. And in the sensor type of data, if the sensor is broken or we have the loss of data transfer, that will introduce missing values as well. And I wanted to note that in the medical data, we're dealing with the 3 dimensions: patient dimension, time dimension, and the feature dimension as well. To illustrate the data itself, we can see that we have 3 dimensions and that each patient can have a different number of time steps, which is the irregular time series data. Now we're going to be talking about different methods proposed for imputation. First one is a long-short time memory. It's a variation of the recurrent neural network designed for time series data. It has 2 states to capture long-term and the short-term dependencies. And we can use it for the imputation as well. For example, on the figure on the right, the missing sample is marked with a red color, and we can feed it to the LSTM cell and connect it with a fully connected layer to get our estimate. Next method, we have piecewise time interpolation. In this method, we treat each patient and each variable independently, and we can use 2 neighboring time points of a variable to impute the missing values. For example, if our missing value, if we have a missing value on Wednesday, we can use the data from Tuesday and Thursday to impute that missing value. Next, we have a cross-sectional imputation method, which is called multiple imputation using chain equations, or MICE. It creates linear regression models to impute the missing value, and as well, it generates multiple versions of imputation, which improves the accuracy. So, for example, if we have the value, the blood pressure value is missing, we can use other variables such as age, heart rate, and weight to impute that missing value. Next, we have the hybrid imputation method, which is called bidirectional recurrent imputation, or BRITS. In this case, we have the bidirectional LSTMs for longitudinal imputation. We can see that we can estimate the missing value on Wednesday using the data prior to Wednesday. And as well, we can estimate the missing value using the data after the Wednesday. And as well, we have the cross-sectional component. And by combining these 2 parts, we can have the better estimates of the missing value. Similarly, we have the context-aware time series imputation, or CATSI. It's similar to BRITS method. However, CATSI has introduced the context vector to capture patients' overall characteristics and temporal dynamics. And the rest of the process is similar. However, with the addition of the context vector, we can have more information towards our estimated values. Next one, we have the longitudinal imputation method, which is NAOMI method, non-autoregressive multi-resolution imputation. It as well utilizes bidirectional RNNs. And the uniqueness about this method is that it's using the recursive divide and conquer principle, where we can use 2 known time steps to impute the value in the middle. And this process is repeated until all the missing values are imputed. Additionally, it's enhanced with adversarial training. The last method for the literature review, we have time-aware multimodal autoencoder used for longitudinal imputation. It utilizes as well bidirectional LSTMs, and as well, it has time-aware mechanism to capture time series information. So to address Dr. Rogers' concern from the proposal, we're going to be talking about different missing value types. First one, we have the missing completely at random missing type, or MCAR, where the missingness is independent of the observed or missing data. And generally speaking, it's an unrealistic scenario. Next one, we have missing at random, or MAR, where the probability of the missing data depends on observed data. Lastly, we have missing not at random, or MNAR, where the missingness depends on the unobserved values themselves, and is the most challenging and most common in the real world settings. Next, we're going to talk about the problem statements. Every missing value imputation algorithm needs some initial estimates of the missing values. As we said before, machine learning models cannot operate on the data with missing values, so we need some initial estimates. Next, we don't know the performance of the long time series against the short time series. We don't know the trade-off between cross-sectional and longitudinal imputation. As well, people didn't study enough the differences between missingness types and the percentages, especially in time series imputation. And once we impute the data, there is not a lot of studies to measure the performance on the downstream tasks, for example, regression or classification with an imputed data set. Lastly, in the research, proposed time series models or methods are tested usually with 1 or 2 data sets, which is not enough to evaluate the method itself. And that is leading to our contributions of our thesis work. First of all, we're going to investigate the effects of different initialization methods for imputing missing values. Second, we're going to study the effect of length of our time series data. Then we're going to study the effect of cross-sectional imputation, longitudinal imputation, and their hybrid learning as well. Then we're going to study the effects of different missing types and percentages as well. And lastly, we're going to see the effects of the downstream tasks on the imputed data set. Next, we're going to be talking about the experiments that we are using in our work. First of all, we're going to be comparing missing value initialization methods. We have 4 different methods. First one is mean, then we have median, piecewise interpolation method. We use it for initialization as well. And we're proposing the variation of the delta initialization method, which is the weighted contribution of mean and the next time variable. Our second experiment is an investigation of the time series length effect. We're going to truncate the time series to 5, 10, 15, 20, and 25 time steps. Third experiment, we're going to see the effects of cross-sectional, longitudinal, and hybrid imputation methods. For the cross-sectional imputation, we're using the MLP part of the Kazijevs method, and as well, we're using 2 variations of grading boosting trees regressors. For longitudinal imputation, we're using LSTM component, Kazijevs component of LSTM, NAOMI, and TAME method. And for the hybrid imputation, we're using BRITS and Kazijevs. Fourth experiment, we're going to see the effects of different types of missing values, as we said, MCAR, MAR, and MNAR. And as well, we're going to be introducing missingness ourselves with the percentages ranging from 5 to 80%. Our last experiment is the classification of the imputed data. So we're going to create the missingness of 5% and 20% of the MCAR type, and we're going to perform the classification task. For to evaluate our methods, first of all, we're going to be using 5% missingness completely at random for our experiments. We're going to be using 80% of the data to train our imputation model parameters, and the rest 20% of the data is going to be used to test the trained models. For the evaluation of the performance, we're going to be using widely adopted metric in the healthcare setting, which is normalized root mean squared deviation, or NRMSD. In this metric, basically, we're taking the difference between actual and imputed value, we normalize the value, and then we're going to be taking factors only of the missing values, because we're interested on the imputation value performance. For the classification performance, we're going to be using weighted F1 score with a rationale that is more robust towards imbalanced data set. Next one, we have collected 5 different data sets, health-related data sets, with a varying sample size, with a varying number of variables, and with a varying number of time steps. And they're coming as well from 3 different domains. For example, DACME, sepsis and hypertension data sets are EHR type of data, and IEEE PPG and heartbeat are the signal type of data. As well, important note that in IEEE PPG and heartbeat dataset, we're truncating the time series to 50 time steps. For the first experiment, we have the results of effects of initializing missing values. We obtain the normalized root mean square deviation across 6 imputation models. And as we see, DACMI dataset is the best initialized by the median. Sepsis and hypertension are the best initialized by the mean. IEEE PPG by the piecewise, and heartbeat by the delta initialization method. However, NAOMI method deteriorates the imputation accuracy by a big margin. If we disregard NAOMI results, we will see that the piecewise method is the best for DACMI, heartbeat dataset, and IEEE PPG dataset as well. Next, we as well performed the experiment to determine the best pairs of the imputation methods and their initialization technique. And we can see that the piecewise interpolation initialization is the best in 4 out of 5 datasets. To show the scope of our experiment, this is a table where we performed all the possible experiments with different initialization methods, with different imputation methods, and on each dataset. Next, we're going to be talking about the results of effects of time series lengths. For the sepsis dataset, we found out that the BRITS is the best imputation model for all the time steps. Similarly, for heartbeat dataset, CAT-C imputation method is the best for all the time steps. For IEEE PPG, CAT-C and CAT-C LSTM are performing the best, depends on the time step itself. For DACMI dataset, CAT-C is the best. And for hypertension dataset, BRITS or CAT-C is the best as well. And interesting observation, the cross-sectional method, CAT-C MLP, performs good when the time series is short. For example, 5 time steps is best in 2 out of 5 datasets, and it's best in 1 out of 5 datasets when the time series has length of 10 time steps. An overall observation that the CAT-C performs best with 15 or more time steps. Next, we're going to see the effects of cross-sectional versus longitudinal versus hybrid imputation. We're just taking the general observations of our results here. For the DACMI dataset, 8 variables are best imputed by the hybrid imputation methods, and 5 of them are best imputed by the longitudinal. In sepsis dataset, 17 are best imputed by hybrid imputation methods, 1 by longitudinal, and 12 by cross-sectional methods. And we have found out that those 12 variables have a correlation with other variables greater than 0.6. In the hypertension dataset, 8 variables are best imputed by hybrid methods and 1 by cross-sectional, and it has a correlation score of 0.8 with another variable. In IEEE PPG dataset, all variables are best imputed by longitudinal methods, and we found out that this dataset is really poorly correlated. The max correlation is 0.31, which explains why hybrid or cross-sectional methods are not performing well enough. Heartbeat dataset has many variables, 61 variables. Out of them, 25 are best imputed by hybrid methods, 22 by longitudinal, and 14 by cross-sectional methods. And we wanted to note that this dataset is highly correlated dataset. And as well, you can refer to the tables in the thesis to see all the results. Next, we're going to be talking about the effects of missing value rates and types. For the first one, we took the MIR and MCIR because the results between them are similar. So for the DACMI dataset, we found out that CAT-C performs best when we have low missing rates, less than 50%, and BRITS when we have high missing rates, more than 50%. Sepsis dataset, on the sepsis dataset, BRITS performs the best for all types and missing rates. TAME performs good on hypertension dataset when the missing rates are between 30% and 70%. For the heartbeat dataset, CAT-C method is the best. And for the IEEE PPG dataset, TAME performs the best when the missing rate is greater than 30%. For the missing not at random type missingness, we found out that BRITS performs the best with DACMI dataset, with sepsis dataset, with hypertension dataset on almost all missing rates, especially when the missing rate is less than 40% and greater than 60%. In the heartbeat dataset, BRITS is performing well as well when the missing rate is less than 70%. And using IEEE PPG dataset, we found that TAME performs the best when the missing rate is less than 40%. And on greater missing rates, BRITS performs the best. Our last experiment is classification of imputed data. So we're using gradient boosting classifier to train the samples with no missing values. And we perform 2 experiments with 5% missingness and 20% missingness. We find that BRITS dataset imputed by BRITS, in this case sepsis, has the best classification accuracy. For the hypertension dataset for 5% missingness, BRITS and CAT-CLSTM provide the best classification accuracy. And for 20%, CAT-C and TAME provide the best classification accuracy. For heartbeat dataset, for 5%, we have LSTM works the best. And for 20% of missingness, CAT-CLSTM works the best in our case. As well, we want to mention that the BRITS is the best imputation method for sepsis dataset. And for hypertension dataset, BRITS and CAT-CLSTM is the best for 5% missing rates. And for 20%, CAT-C and TAME has the best imputation results. Sorry, not the best, but they're second and third best. An interesting observation that the heartbeat dataset has better classification using LSTM and CAT-CLSTM, and it's better than the ideal case scenario when we don't have missing values. So the last thing in the presentation is the conclusions. So we found out that there is no best method for each data set. For EHR or electronic health records type of data, such as NAOMI, sepsis, and hypertension, CAT-C or BRITS methods are work the best. And for the signal type of data, CAT-CLSTM or piecewise interpolation works the best. Piecewise interpolation itself is the best initialization for 4 out of 5 data sets. When we have our effects of time length experiments, we found that CAT-C is superior when the data has a time series length of 15 or more. In general, hybrid methods show the best imputation for imputing individual variables. And the performance of imputing different missing types, such as MAR, MCAR, and MNAR performance is different. Imputation of MNAR has higher error, and EHR and medical data are often MNAR type. And as we saw, this is the most challenging type to impute in missing values, and it's the most often in the real world data. And BRITS method generally yields best imputation for MNAR type of data and performs well on higher missing rates when we're using MCAR and MAR type of missingness. And the last observation that the better imputation leads to a better classification of accuracy. We as well had the publications to make this thesis work happen. For example, we had the prior knowledge in time series modeling, and we published the conference paper in the ICHI conference. And this thesis work contributed to a journal paper submission in the Journal of Biomedical Informatics, and is currently published to archive. As well, we have the references, and thank you.